You may have already heard that in the coming weeks we might see a new star appear in the sky. The star is called T Coronae Borealis, a small star usually invisible to the naked eye in the constellation of the Northern Crown. Every 80 years or so for a few days, this star goes through a nova phase, becoming much, much brighter. During these occasions, this star becomes not only visible to the naked eye but also under light-polluted city skies. But what is happening? How can we be quite sure it will happen in these months, and what is really going on at the stellar physics level? We'll discuss this calmly in this video, where we'll try to shed some light on this. Just before midnight on May 12, 1866, Irish astronomer and naturalist John Birmingham was walking home in the town of Tuam in County Galway, Ireland. Looking up at the sky, Birmingham realized there was something very strange and unexpected that he had never seen before. A new star had appeared in the constellation of the Northern Crown. It was a familiar constellation he had seen many times before, so it was strange that a new star had suddenly appeared. He immediately understood that it must be a nova, a new star, as it had been called for centuries. But it was very strange that he was the first to observe it, and no one else was aware of it. More investigation was needed, so Birmingham continued to observe and study it over time. He then decided to write to the London Times, a newspaper of the time, to inform the scientific community of what he had observed. The editor of this newspaper, with a hint of racism towards the Irish, decided to discard his letter because he believed it was impossible for an idle Irishman to have discovered this object first, when the learned English astronomers had not been able to observe it. At that point, Birmingham contacted another astronomer directly, the Londoner William Huggins, who could use spectroscopic techniques to analyze the composition of the new star he had observed. Huggins, observing the nova in the following days, noticed something extraordinary. T Coronae Borealis had expelled a hydrogen gas that was expanding from the central star. His hypothesis was that in this identity we saw as a nova, T Coronae Borealis had given rise to the brightest nova since the one observed by Kepler in 1604 in the constellation of Ophiuchus. This explosion was very important for the history of astronomy because it was the first time we saw a nova corresponding to an already known star. T Coronae Borealis was already known, but it could only be seen with telescopes. So we knew which star had brightened, giving rise to this phenomenon. It was a unique opportunity to study this nova phenomenon that had remained a mystery until then. But what was happening? Why had this star suddenly emitted all this hydrogen, leading to this enormous increase in brightness? And above all, to return to our initial question, why do we think this phenomenon is about to repeat in the coming weeks or months? Before we continue, please like the video to support us with the YouTube algorithms. Also, you can subscribe to the channel and activate the bell if you haven't already so you don't miss the next content we'll be posting. Let's now return to the new T Coronae Borealis. The phenomenon observed by Birmingham happened again about 80 years later, in the mid-1900s. In 1946, it again put on a show, becoming visible to the naked eye as it had been for Birmingham. When this star appears, it is quite easy to find because provided you have a sufficiently dark sky, the Northern Crown is perhaps one of the easiest constellations to recognize. Its shape is unmistakable as its main stars form a beautiful luminous arc. In mythology, this arc of stars is a crown that Dionysus gave to Ariadne. None of the 7 stars of the Northern Crown is particularly bright. The brightest is called Alphecca, which has a brightness similar to that of the North Star. T Coronae Borealis, often abbreviated as TCRB or T Corbo, is located very close to the arc of the crown. But in general, it cannot be seen at all with the naked eye because it has a magnitude of 10, and 10 is definitely invisible. Even with binoculars or a small telescope, it is difficult to see a magnitude 10 star. The naked eye visibility limit is about 6, so 10 is a much, much darker object, thousands of times darker than a magnitude 6 star, barely visible to the naked eye. And all in all, it's not really worth looking for because you won't see much. You'll see a completely insignificant star, like many others you can see in the starry sky. The difference from many other stars, however, is that every 80 years or so, its brightness increases dramatically. This star reaches a magnitude of about 2 or 3, so again comparable to Alphecca or the North Star, and this will also happen with the next explosion, which will occur 80 years after the last one, so between 2024 and 2025. The explosion of such a nearby and known nova is something very precious because we know it is coming, we know when it will arrive, and this allows us to start studying it well before the explosion. to see all the preparatory phases that lead a seemingly normal star to explode as a nova. Due to these sudden explosions, T Coronae Borealis has also earned the nickname Blaze Star. Because of these flares it produces once every 80 years. But exactly what is happening? Why do these explosions occur, and why do they occur every 80 years? T Coronae Borealis is actually not a single star, but a binary system located about 3,000 light-years from us. This binary system is very peculiar because it is a so-called symbiotic system, where the two stars are so close to each other that they greatly influence one another, so much so that one star can be said to eat the other. The two stars in the system are a white dwarf and a red giant. The red giant is a star that, having finished burning hydrogen to produce helium in its core, expands and swells to find a new balance. The hydrogen then remains in the outer shells of the star, while fusion of helium may eventually occur at the center. In the outer layers, the temperature and pressure are not sufficient to fuse hydrogen, which therefore remains there in this sort of large atmosphere of the star. On the other hand, the white dwarf is what remains of a dead star, so to speak, the core of a star similar to the sun stripped of its outer layers. No more thermonuclear reactions occur in the white dwarf because the temperature is not sufficient to continue burning elements up to iron. So a white dwarf is essentially a dead star where no nuclear reactions take place. The core has compacted to form this dense object that will continue to cool for eternity as long as the universe exists. But in binary systems like this, something very peculiar happens. The white dwarf and the red giant are very, very close to each other. The white dwarf is a very compact object with strong gravity, while the red giant is a very expanded object where the outer layers have very low density. This material from the red giant, the outer shells of hydrogen, can thus reach the Lagrangian point L1, the first Lagrangian point, where the gravitational forces of the white dwarf and the red giant balance each other. This means that when this gas crosses this L1 point, it enters the gravitational influence of the white dwarf, leaving the red giant and moving towards the white dwarf. The white dwarf then steals material from the outer layers of the giant, which accumulates in a disk around the white dwarf. When enough material has accumulated, a critical mass is reached where the temperature and pressure of this material around the white dwarf becomes so high that thermonuclear reactions of hydrogen can be triggered. The trigger occurs with a sudden eruption linked to the fact that the first nuclear reactions that start increase temperature and pressure, causing other nuclear reactions and so on, in a cascade, a chain reaction that suddenly causes the luminosity of the white dwarf to explode, becoming extremely bright, creating a nova phenomenon. But not only that, because once the nova has occurred, this process will actually continue, and so material will again begin to accumulate around the white dwarf, stolen from the red giant. So you understand that there is a fairly predetermined time, given a pair of a white dwarf and a red giant, for enough material to accumulate to reach the critical mass. We expect novae to recur regularly, in this case every 80 years, and these novae are called recurrent for this reason. We know they happen every 80 years because we have already seen two such events for T Coronae Borealis in 1866 and 1946. The next one, therefore, the 80 years, expire just before 2026. By analyzing the data from 1946, astronomers realized that about a year and a month before the explosion, there is a reduction in the brightness of this star. It is the material surrounding the white dwarf that makes it darker before the nova is triggered. Amateur astronomers and members of the AAVSO, the American Association of Variable Star Observers, noticed this brightness reduction in March 2023. If it behaves as it did in the 1940s, T Coronae Borealis would have exploded last May, with some uncertainty, of course, by a few months. So it means it didn't explode last May, otherwise this video wouldn't make sense. But it means we can expect the explosion to happen in the coming months, probably by this summer. We expect it to happen in the coming months, but we don't know exactly when, probably by the summer, at most by the fall of 2024, but almost certainly not beyond early 2025. This could be a bit critical because the northern crown is not visible at all times of the year. It is visible for much of the year, but actually in the winter months, it is not visible because it would be too close to the sun. And so if the explosion occurs during the day, we would not be able to see this nova, which would be a pity. To find the northern crown, I recommend learning to recognize it on summer nights when you might already be watching shooting stars in the mountains or on the beach, wherever you like. And if the place is dark enough, You can then see these 7 medium brightness stars that form this beautiful arc of stars. It is really easy to recognize if the sky is dark enough. You can also help yourself with a planetary app like Stellarium or Google Sky Map, but the experience with the real sky is always the most precious. Let's keep our fingers crossed and hope the explosion happens this summer, because it would certainly be a wonderful spectacle to witness. Thank you for following me this far, and we invite you once again to subscribe to the channel and activate the bell.